Hi everyone, welcome back to RAG course. Today we are going to discuss about data preparation. In the previous sessions we discussed the RAG basics and the high level of RAG architecture, and after that data loading and the different ways of loading and the different data sources we discussed. So today the next important topic is chunking and embedding. We can discuss chunking today, and in the next session we can discuss like a different embedding techniques. So when working with the long documents in a RAG system, the text must first be pre-processed so it can be stored and retrieved effectively. So why chunking is necessary? Large documents are broken into smaller chunks before being added a vector database. This is done because large models have limited context window. Smaller chunks are easier to retrieve accurately. Fine gradient retrieval improves answer quality. Each chunk should be small enough to be processed independently and large enough to preserve meaning. So from chunks to embedding. After chunking, each chunk is converted into a embedding vector. The embedding captures the semantic meaning of the text. These vectors are stored in a vector database. So semantic meaning and embeddings we can discuss in the embedding topics. So retrieval during retrieval, the system compares the embedding of a user's question to store embeddings and find a closest matches based on vector distance. What makes a good chunk? Chunking works best when each chunk contains one clear piece of information, can be understood on its own. It doesn't rely heavily on surrounding text fra- for context. If a chunk depends on previous or following sections, retrieval quality suffers, even if the embedding similarity is high. So, the core challenge here, the main challenge in pre processing is creating chunking that are both semantical meaning and context independency. A robust ingestion pipeline, typically clean raw test, is like a removing noise, formatting artifacts and relevant content. Split the documents at natural boundaries like a paragraph, sections or sentence. Produce chunks that stand alone and retrieval well. Good chunking is one of the most important factor in building accurate and reliable rack system. So you can see the workflow diagram is documents and processing and metadata, technical and terms, observations, summaries and hypothetical question. These are like a different highlighted content in the data. And now chunking, like a recursive chunking, document specific chunking, we have like a different chunking process here. So recursive chunking, document specific chunking, semantic chunking, agentic chunking, like a different chunking so we can utilize, and that is converted into the embedded model which will store into the vectors. So text preparation replace observations and clean the text. Metadata collection store page numbers, sources, and others, something like that. And test splitting is a player characters, recursive, semantic, or agentic chunking. And the goal is produce clear, unambiguous chunks that don't require surrounding context to store useful metadata with each chunk to enable filtering during retrieval, making the process both faster and more accurate. So, adding metadata to enable metadata filtering that we can discuss now. You want to store metadata alongside the text chunks in your vector store so that retrieval can apply metadata based filtering. So, without metadata, retrieval really relies only on semantic similarity, then makes it difficult to restrict the result to specific document or source. Filtered by time, author, or document type, apply business or domain specific constraints. So solution is more metadata together with each text chunk during ingestion. This enables hybrid retrieval, combining semantic similarity with structured filtering. Metadata can come from three main sources. One is a metadata extraction or enrichment stage. Extract existing document metadata. Start with metadata that already exist in the source document, such as author, title, creation or modification date, or else data type or source system. So this information is often available in file headers, databases or document management system. The second one is add computed metadata. So next, the computed additional metadata fields during ingestion. For example, file location or source path, file size, page count, text length or token count, chunk index within the document. Computed metadata helps with the debugging, ranking, filtering, and traceability. Now, the optional one is a generate context-based metadata with LLM. So, for specialized use case, you can enrich chunks with LLM generated metadata such as topic labels, summarizers, keyword or entities, sensitivity or compliance flags. So, this step analyzed the document text itself and added higher level semantic structure. So the what is the fourth one is just like a store metadata with the each chunk. Finally, save the metadata together with the text chunk and embed it embedding in the vector store. At query time, this allows you to filter result by metadata, example data range, document type, combines filter with the vector similarity, improve precision and control over retrieval behavior. What you can take away from the explanation? Metadata transform a vector store from a pure similarity engine into the controlled retrieval system. Well designed metadata enables better filtering, higher precision, and more reliable RAG pipelines. So you can see the one of the flow. So this is the document read existing metadata from the digital file and define additional metadata, generate metadata from the text. So save metadata along with the embeddings. You can see the metadata and embeddings and split into the it is like a loop. It is splitting and there's like a chunks and this is like a metadata. Both are we are storing and based on the user request we are searching by using the filtering by using the metadata. And now coming to the implementation, these are like a different type of packages we are going to use in the hands-on. One is the PyPDF we discussed in the data loading, Pandas, Pydantic, OpenAI, Matplotlib, Scikit-learn. So Python docs for documents, NLTK, LangChain, OpenAI, LangChain experimental, and Python doc. These are the required packages for running our code. So now setting up samples files like I have data set I will upload in my Git repo. You can utilize that. So otherwise you can use your own data sets to check this. Now, setting up API secret key, I already explained in the first video. We required OpenAPI key. You can go to the OpenAPI website and generate a key, or if you are using Anthropic key, you can use the same and Google API key, whatever you want. Load in the environments and get it back to your code. So now metadata extraction and filtering we can discuss. So for metadata extraction, we are loading the Python PDF file using a PyPDF2, loading the file and PDF reader, PyPDF2.pdf reader, metadata is equal to reader.metadata. So now we are going for page in reader.page and taking extracting the information. You can see the information come like this: author, creation date, creator, keywords, more date. So these are like a different headers in the PDF page. So now metadata extraction we are doing like a page count, file size, file name, file path, and file text length. This is another metadata text we are extracting here. So this is like a different text. Now, pyramid import base model we are taking, and we are calling the client and OpenAI and other contact. So name and company email, we are giving contact details. So extract the contact information of all others. This is like a system message for us. Now we are calling client beta chart completion pass. So model we are using a GPT-5 mini, and role is a system and giving a system and a message and user and a text. Response format is contact. Now we are what we are doing, other contact and response dot choice dot message pass, and metadata we are giving like a dictionary. So now other contact equals to other contact, and LLM extracting the information from the metadata text. So this is like a other contact, and taking the contact and get extracting the information. So this is the one way of uh, metadata filtering and generating the text. Now, how metadata filtering works in vector search? Metadata filtering improves retrieval quality by narrowing the search space before semantic similarity calculated. So instead of comparing a query against all vectors in the database, the vector store applies metadata constraints first. So other equals to Smith, and Smith or date is greater than or equal to 2023. So this is like applying metadata constraint first, and then runs semantic similarity search only the filter subset. By reducing the candidate set, the system avoid retrieving text that is semantically similar but contextually irrelevant. So now we can discuss why metadata filtering matters. Similarity alone can be misleading. Different documents often use the same word to mean different things. So metadata filtering helps reduce false positive, improve precision, and make retrieval behavior more predictable and controllable. When to use metadata filtering? Metadata filtering is especially useful when your data naturally falls into the distinct buckets, and users usually care about one bucket at a time. So common scenarios we can discuss now: multiple departments in the one index. Example: HR, engineering, and finance documents stored together. So filter is like a department equals to engineering before searching. Now, time-based document collection is like a content indexed across multiple years or quarters, like a filter to year equal to 2024. When the user asks about last year, so now mixed content type. Example: manuals, sport tickets, and emails. Filter to source manual to avoid pulling information. Support charters. Overlapping vocabulary. So example: the word is a release appears in product document and press release. Filtered by document type to misambiguate meaning. What points take away from this explanation? Use metadata filtering to limit what the vector search can see before asking which of these most similar. This coordination of structure filtering and semantic similarity is one of the most effective way to improve RAG retrieval accuracy. So you can see the flow. So user asking a question: what are the benefits of using antioxidant? So select knowledge base, This is like a medicine knowledge base, and environmental engineering is a knowledge base, like a two knowledge bases. Treatment with antioxidants has the potential to reduce oxidative damage in cells. So the use of this plastic can slow down their degradation by oxidative processes. So I'm sorry, enhancing data quality by replacing abbreviations and technical terms. You want very text chunk every text chunk in your vector store to be self explanatory, so it can be understand as a standalone price piece of information. The solution use regular expression and llms to expand abbreviations and clarify technical terms before generating embeddings. This makes text chunks self explanatory when stored as a standalone piece. Data quality enhancement, so abbreviations expansion. So you want every text chunk in your vector store to be self-explanatory, so it can be understand as the standalone piece of information. The solution is like a use regular expressions and LLMs to expand abbreviations and clarify technical terms before generating embeddings. So this makes text chunks self-explanatory when stored as standalone piece. So you can take the example import abbreviation dictionary NLP, RNN, LSTM, GRUTF and multi-head attention. So feed forward network. So now this is file path we are going to block first transformer dot text and loading. So we are giving for abbreviations and full form. In abbreviation dictionary dot items, then text we are bringing those from abbreviation. So same as you can see the OpenAI, we are giving taking the text. So loading the file and giving the prompt. The text below contains a financial report including a lot of abbreviations and technical terms from the finance domain, and please replace the abbreviations with their full form and provide a brief explanation of the technical terms, so the whole text get arranged to read and understandable for everyone. These are like a prompt and often used abbreviations, or we are giving like some instructions as well. Dots strip. So now you can see we are using a chart completion from OpenAI, and then providing a role and content and model name. So and then printing the message. So here you can see the Europe, Middle East and Africa drives big sale jump into the quarter two. So this is like a content we are providing based on generating. LLM is generating by using the prompt and given the text. So this is another example is like expanding abbreviations and rag chunking. When abbreviations are expanded and technical terms are clarified, each text chunk become understandable on its own. This matters because rag system retrieves chunks in isolation. During retrieval, the embedding model only see the words inside a chunk. It has no access to surrounding context. Vague or abbreviated terms provide less semantic signal. For example, NLP is far less information than natural language processing. Use often such with a short or mixed language queries, and embeddings work better than both the abbreviations and expanded form appears in the text. Why this works? Expanding abbreviations improves retrieval quality for several reasons. Embedding built from expanded terms contains richer semantic meaning than acronymy alone. Queries like NLP, large models, or text understanding still match chunks that include natural language processing, and retrieved chunks are easier for the LLM to interpret without guessing what an acronym meaning. This reduces ambiguity at both the retrieval and generation stage. When to use abbreviations explanation. This technique is especially helpful for technical documents filled with acronym, financial or legal reports that rely on shorthand, medical or clinical text, any document intended for reading outside the original expert audience. When not to use it, abbreviation expansion is not always appropriate. Avoid it when abbreviations are the standard or universally understand form. Example like a HTTP in web development. Processing every language collection would be too expensive, or documents must be ingested in the real time with extremely low latency. What are the takeaway points from the explanation is like expand abbreviations when it improves clarity and semantic signal. The goal is to make each chunk self-contained, searchable, and easy for both embedding models and LLMs to interpret. So, improving search accuracy by creating hypothetical questions for text chunks. You want to improve retrieval quality by comparing the user questions to hypothetical questions derives from text chunk instead of comparing it directly to the text chunks. Solution is the processing and indexing steps as well as retrieval and runtime in the RAG app. Before indexing the data, you need to load the data and split into the chunks. Iterate over the chunks and generate at least one hypothetical question per text chunk. Generating embeddings for each hypothetical question, store the hypothetical questions and their embeddings in the database. So this is the workflow. You can see the load text document and split into the paragraphs and go to the LLM, generate hypothetical questions and go to the embeddings and save hypothetical questions plus embeddings. So now go to the vector store and metadata. It contains original text chunks and um, link to original document. So now similarity search and hypothetical questions. It will go to the build prompt. It will build prompt and original text chunks and return the generator answer. Each hypothetical questions link back to the original text chunk during runtime of the RAG app. The retrieval search the hypothetical question, but typically the understanding text chunks are what you pass to the LLM. So the model receives the full context rather than only the derived hypothetical questions. So now hypothetical question embedding for enhanced retrieval. So you can see the PDF loading and file opening PDF2 and getting the headers of a page reader and extracting the information, and then using a Langchain text splitter. It contains like a recursive character text splitter. Here we are using like a separator. Based on that we are getting the text chunks. Now you can try in your notebook, and now we are passing this content to the prompt. So using OpenAI, Pandatic kind of base model, loading the test document, and then open the OpenAI text wrap.detent. Is like a below you can find the chart history between two students and hypothetical questions, and we are giving a question and a client dot uh, beta chart completion we are providing, and role and prompt we are giving. Along with that response format is like a hypothetical questions. So then you can see the uh, how would you implement wrap that can reduce manufacturing costs. So these are like a different hypothetical questions. Now character based document splitting we are doing. So splitting by character and giving the chunk size and all. So we are splitting the characters like this. Now recursive text splitting method. We are using a recursive text splitting method on top of the data. So then document array splitting. So giving the document, and this is like a document array splitting using a Langton text splitter and Python code splitter, latex text splitter, markdown header splitter. So we have like a different splitters are that you can utilize in the code. So you can see the data like this, and then go to the next step, semantic aware text chunking. Semantic aware text chunking to you can use the Langton experimental text splitter, semantic chunker, and use the OpenAI embedding model. Then utilize the text splinter and OpenAI embeddings, and you can do the embedding and splitting. And now, next, agent text chunking. Agent text is chunking here, providing the proposal indexing and GPT model, and then sentence, and giving LLM with the structured output sentence we are providing, and then we are giving like a extraction chain dot invoke. So this is like a agent we are using that. So for a sentence, proposition dot sentence, you can get it like this. So these are like a different chunking methods we have used. One is the agent text chunking, and semantic aware text chunking, document aware splitting, recursive text splitting method, and character based document splitting. So we have like a lot of based on our requirement. You can go through the chunking part and run the code. So in the next session, we can discuss about the text embeddings, like what is the embedding technique, why we are using in the rack system. This discussion we can do it in the next sessions. So first one, data loading for the rack system, and second one, chunking we discussed, and now third we are going to discuss embeddings. So please subscribe my channel to get more videos, and you can follow this RAG complete course. We can meet again in the next session in the text embeddings. Thank you. Have a nice day.